Hello everyone. As I said in the last video, I wanted to make something talking about the LRU reference matrix. So before I get started, it's going to be, it's very important to understand why reference matrices are even covered, because it seems sort of trivial when LRU is pretty basic to understand. So let's just look at an example here. Let's say we're looking at a four-way set associative cache with, and we're going to look at just a single index. So if we consider this to just be one of the single indices, then it's going to have four different lines in it, each with its own tag. Right. So the idea here is, remember that whenever we're going to access something, we're going to eventually end up putting it into this cache. But what if let's say we're accessing a whole bunch of things at this same exact index here, right? What happens when you access an element? It's not in the cache, but the cache is full, right? So if there's data in all four of these locations here, which one do you replace? And as I had mentioned in the video about cache, the typical thing to do, and one of the best methods, is least recently used. So then you need to ask yourself, how can you implement that? How can you physically implement what's the oldest? And that's where the reference matrix comes in. So if, let's say, we consider this to be like location 0, location 1, location 2, and location 3 in the set, well, then the reference matrix we can draw like this. It's going to contain information. So if I could draw out the full grid here, hopefully that will help a little bit. And we have a line coming straight through the diagonal. So we're not going to use any of these bottom squares. We're not going to use anything on the diagonal, so we're only going to use these top ones. You might also see the reference matrix getting drawn like this. And this is just for conciseness, because it uses up less space, but it's the same exact thing, right? In this case, you would just not use these three, but you still have, 0, 1, 0, 1, 0, 1, 1, 1, 1 isn't used, right? So they're basically the same thing. And this is particularly for four elements, like for a four-way set associative set. You can have a reference matrix for any size. You could have all the way from 1 to an infinite amount of elements, essentially. So the reference matrix here basically just contains the minimum amount of information to be able to reconstruct the entire history of what's happened in this index. And if you can reconstruct the entire history, then you know what the oldest is. And it's a little bit bizarre when you're first learning about it, but the key thing to this, to getting used to how the reference matrices work, is just practice. Just doing problems and making sure that you have the rules down so that you don't have to think too hard while you're actually running through an example here. So the best way probably to look at the reference matrix and figure out how it works is just going to be for me to run through an example here. So let's say we have, we're going to access tags 2, then 9, 12, 7, 2, 45, 18, 2, 45, and 18 in this order. And so here we're just assuming that, let's say, the index for all of these is identical. So we're accessing some memory address where the tag is 2 and the index is something. And then here we're accessing an address where the tag is 9 and the index is the same thing. And the index is going to be exactly the same thing. And these are just the tags. And then again, the word and the byte portion don't really matter for what's in the cache. It just matters for how you get the information out of the cache line once you have that. So we need to start off with a reference matrix. And typically what you do is you start off with an empty reference matrix, but that doesn't really make any sense. From the perspective of hardware, the reference matrix, each of the elements would have some data in it, right? It couldn't just be empty. It's going to be a 0 or a 1. And because of that, we need to figure out the starting configuration. And it turns out that, and here also I should mention, we're going to be looking at a reference matrix just with 4 elements. So like a 4-way set associative. But yeah, we need to figure out a starting configuration. Because then we can just use the same rules for everything. So again, we're going to cross off the diagonal, and we're only going to use the top here. So it turns out that if we start off with all 1s, that's essentially equivalent to starting out empty for the rules. So the rules for doing the reference matrix. The oldest thing has 0s across, 1s up. And what I mean by that is, here, if we look at, let's say 1 does not only have 0s across and 1s up here. So when I say up, I mean look at the column corresponding to that value. When I say across, I mean look at the row corresponding to that value. So here we can see 3. 3 is 1s across and nothing up. So 1s across, that's not the oldest. 2 has 1s across, 1 has 1s across. 0 has only 0s across and 1s up. There's nothing here, but, I could say, I have a box of things. That box is empty, and everything in this box is worth $1 million. That's a true statement. It doesn't really mean anything, but it's a true statement. So we can say here that there's 0s across and 1s up for 0, which actually means that according to this reference matrix, we know the oldest thing is 0. We don't really need to know, what the next oldest thing is, because the whole point is that we want to be able to reconstruct everything simply from the reference matrix. You don't really want to look at previous things and say, oh, okay, well, because of how LRU works, I know that this is going to be in the cache or something like that. You really want to look at the reference matrix at the current stage that you're at to figure out what to do next. And that's because that's the whole point, is the reference matrix is changing over time, and you can't just magically look at all instances of the matrix in time. So we'll start off here. Or additionally, you can just start off empty. It just makes it a bit easier if you start off with this to see how everything needs to be laid out. So the first thing that we're going to do is access memory location 2. Or actually, over here as well, I'm going to have my cache, cache set. So for one of the particular indices. And then I'm going to have location 0, 1, 2, and 3 in the cache, right? And these correspond to these 0, 1, 2, and 3. And so whenever we access data, we're going to be putting whatever this tag is, as well as that data, in one of these locations in the set. And we need, and then we're using this reference matrix here to keep track of what the order of everything goes in. So if we're checking to see, is 2 going to be a hit or a miss, we're going to look in the cache set to figure out if that tag is there, meaning that the data is in the set. So first thing, going to access 2, we can look in our cache and say, well, 2's not in here, not this 2, right? I'm talking about a 2 tag, which I would put over here. It's not in there, so this is a miss. And when you have a miss, you're just going to determine the oldest thing in the cache, which here we already have is 0, and that's where you're going to put 2. So 2 is going to go in position 0 here. The next step would just be to update the reference matrix properly. So when you update, you put 1s across and 0s up. So you do the exact opposite, and you want to make sure you're not mixing which of these is which. Because otherwise, technically it'll work if you swap this and you say 1s across, 0s up, and then 0s up, 0s across, 1s up. It'll still work. It's just completely inverted. So you just want to make sure you're using this implementation here. So start off with all ones and continue from there. So access 2, and then we'll have our next reference matrix here. So the first thing that I do is when I update, I do the update first. So I've got here, and I'm just going to draw it like this from now on, with ignoring the grid. But if you need to take a look and see where the values actually are, you can just look in this grid here. So we're in location 0, I'm going to put 1s across. Well, there's no locations across, and then 0s up. So I'll put 0s up here. And then for the rest of the locations, you just copy over what the value is. So the rest are 1, so they'll just stay as 1. And that's it. So now what I typically do is figure out the oldest. The first thing I do is just figure out the oldest so I know about it and don't have to compute it later. So here, again, looking for 0s across and 1s up. So if I look at the 1 column here, 0s only across and 1s only up. So the oldest here is 1. And that's sort of why this reference matrix is the best starting one, is because the oldest is 0, then it's going to be 1, then 2, then 3. So that's why it correlates to starting out with an empty matrix, whatever that means. So then we'll go ahead and access 9. Look in our cache here, we see 9 isn't there. So that means this is a miss. And so we're going to put it in location 1 because it's the oldest, and then move on. So again, we're updating location 1 because we just put something in location 1. So we're going to put 1s across and 0s up, and then copy the rest over. And now, if we look for what the oldest thing is, well, 2 here has 0s across and 1s up. So 2 is the oldest. And then I'll keep going down here. So the next value that we're trying to access is 12. Well, look in the cache, 12 is not there. So this is a miss. And look at the last reference matrix, we can see that the oldest thing is 2. So we can go ahead and draw the new reference matrix by updating 2. So again, at 2, we're going to put 1s across, 0s up. And then we'll just copy over the rest. So 0, 0, 1, we'll have 0, 0, 1 here. And then finally, look at, for the oldest, 0s across, 1s up. So 3s have 0s across and 1s up. So the oldest is 3. And then as well, we want to make sure we're putting stuff into the cache as it goes in. Lastly, we're going to access 7. Lastly in terms of initialization, obviously for these first 4 here, we're assuming the cache is essentially empty, or at least stores information that is completely irrelevant from what we're doing. So obviously we're going to put something in 0, then 1, then 2, then 3, and then it'll start getting interesting after that once we actually get different information. So 7 is going to be a miss because it's not in the cache, so it's going to go in location 3. Then we can update the reference matrix. And again, we put 1s across and 0s up in the 3 column, and then we'll just keep everything else the same. And then we're essentially back at where we started, which makes sense because the first thing that we did was put something in location 0, then 1, then 2, then 3, and so the oldest thing at this point is 0. Is this slot 0, right? 2 is the first thing that we put in here, and now we're full up, so if we're going to replace anything, that's what we should replace. So the oldest here is back at 0. So now we're going to access 2 again. So 2, well, now we look in our cache and we see, hey, there's a 2 right there. So this is a hit. And because it's a hit, you're going to update the reference matrix because you just recently accessed it, right? You don't want to keep track of what's least recently written. You want to keep track of what's least recently used. So here we access 2, so we're going to have to update the reference matrix in that location to say, hey, don't get rid of that right now. Maybe in a little bit, but not right now. So we'll have 3, 2, 1, 0. And instead of looking at the oldest to see where we will update, we have a hit. So we would look here to see, hey, it was in location 0, so we need to update 0. So we would put 1s across and 0s up, and then copy over the rest. And now our oldest, we can see here, 1s across. 1 across has only 0s, 1 up has only 1s, so the oldest is going to be 1. All right, so let's see here. I'll just move up and down for this portion. So the next thing that we access is location 45. So if I move down here, what I'm going to do actually is remove this and then bring this up, and I'll just keep moving along, and so you can just look back through the video to see the full progress. All right, so then yeah, then we have 45. So first thing we do is look in the cache. It's not there, so this is going to be a miss. The oldest thing was a 1, so that means we're going to put it in location 1, which means we're overwriting 9. So 9 is no longer in the cache. And so we'll update our reference matrix. And since we just put something in location 1, we're going to put 1s across and 0s up for the 1. So 1s across and 0s up, and then copy over the rest. So now if we look for what the oldest thing is, it is 2, because 2 has 0s across and 1s up. Then we'll access location 18. If we look in the cache, 18 is not there, so it'll be a miss. Because it's a miss, we're going to put it in location 2. So 18 is going to come right here. And then we can draw out our reference matrix, updating location 2, because that's where we just put 18. So location 2, we're going to put 1s across and 0s up, and everything else is going to stay the same. So now we access 2 again. Well, actually, first, again, let's figure out the oldest. The oldest now is 3. So here, now we're accessing 2 again. 2 is in the cache, so this will be a hit. And so we're going to update location 0. So location 0, we're going to put 1s across and 0s up, and then copy over everything else. And so here, if we look for the oldest again, it's still 3. So 3 has 0s across and 1s up, so the oldest thing is still 3. Which makes sense, right? Because we've accessed 7 all the way back here, and we accessed 2, 45, 18, 2. So all these are going to be newer, more recent than this one. So it stays the oldest, even though it was also the oldest here. All right, we can go ahead and shift that up. For these last 2. All right, so now we access 45 again. But now it'll be a hit. And it's a hit at location 1. So put 3, 2, 1, 0. So we're updating location 1, so put 1s across, 0s up, and copy the rest over. So the rest here are all 0s. And again, if we look here, 3 has zeros across and ones up, so the oldest is 3 still, which makes sense, again, because we're just kind of accessing all of these. And then lastly, we have 18. And 18 is also going to be a hit, because it's in the cache. And so we can go ahead and just update the reference matrix. And since it was in location 2, we'll update location 2. So we put 1s across and 0s up. And everything else will stay the same. And now and this is the end. And so here again, the oldest is going to be location 3 in the set, because 0s across, 1s up. And so this would essentially be the final answer. Really, the whole answer for this would be all sets, because we want to see how it's progressing. But it's relatively straightforward. As long as you remember these two rules and you just keep track of what's going on in the cache, it should be fairly straightforward to just go one to the next, to the next, to the next. Just make sure you're constant every single time, whichever one of these locations you access, you always update. And then you should always look for the oldest based off of what's actually in the reference matrix, as opposed to trying to read back in the list and see what the oldest thing is. But yeah, hopefully that helps you out with the reference matrix.